So that was in 1D. What about in 2D? Because what we're working towards here is, remember, we're working towards a constitutive model, a closure relationship between stress and strain. Well, we know our stress is a tensor, right? It's got 9 components. So just our 1D relationship's not quite going to work. We need something that relates the 9 components of stress to what we'll see is ultimately 9 components of strain. And then, of course, the strain needs to be related to displacements somehow so that we can solve our equilibrium equation. So let's look at it in 2D. In 2D, and the first thing we'll look at is going to be, again, epsilon x, so the strain in the x direction. And we'll just use our regular old engineering definition again, right? So if this is the reference configuration, this is sort of the undeformed configuration. So this is the reference, and this is the deformed. So in other words, I start with a cube or square, and I apply some forces to it, and it translates and deforms into this shape. Okay. But if you notice that we have a bunch of little differentials here, so this is really a differential element dx. This length is dx. It's small, right? And our change is going to be small, right? So that these sort of derivatives hold. They're small changes. Okay. So let's use our same sort of engineering definition, right? So we have, if we look at, we want to look at the change in the line segments here. So in the deformed configuration, we have the magnitude, the current length is the magnitude of the line segment AB. The original length is the magnitude of the line segment AB. And we're going to divide that by that. Right? I'm sorry. We're going to divide it. That would be not the correct definition of strain, right? We want by AB, right? So we want final length minus original length divided by original length. Okay? But our stretch is not just one-dimensional, right? So we stretched it, but it's a sort of a two-dimensional thing now. Right? So AB, if you can't read it, that's dx, right? So we can just go ahead and make that substitution. So we have AB minus dx over dx is equal to AB over dx minus 1. Okay? Or if we solve this equation for AB, right, so let's solve for the magnitude AB, then we have epsilon x plus 1 dx. All right? So the magnitude AB, right, AB is just a vector. I'm just using the points to define it, right? AB is just a vector. It's the vector between the points A and B. And the vertical lines indicate that it's a magnitude. Right? So the magnitude of a vector is the sum of the squares of the components, right? So it would be like AB x squared plus AB y squared. Right? So AB in the x direction is equal to essentially B, the point B, the x component of B minus the x component of A. Okay? So what is B? B is this point, And my reference position is sort of over here at big A, right? So we have this. So to get to B, we have this distance, which is u of x, right? This distance, which is u of x, plus the original length, dx, right? So plus dx plus this distance here, which is defined right here as partial ux partial x dx. All right? And then the point A of x is just this distance here, so it's minus ux. Right? So then the u's cancel, and we're just left with this right there. Okay. So likewise, we'll do the same thing, ABY. So AB is just this distance, but I want to know that I want to know this y component. Okay. So that's just by minus ay, which is equal to uy plus partial uy partial x dx minus uy. Uy's cancel. Right? And so now I have AB, I have ABX and ABY. So I want to take, let's use a different color. I want to take this guy and substitute it there, and this guy and substitute it there, right? And I don't like this square root, right? So in order to get rid of that square root, I'm going to square both sides of the equation. Okay? So I just said, now I say the magnitude of AB squared is equal to just what's under the radical. And so I'll move down here. I say AB squared, and I'm just going to plug in, right? So then I just have dx plus partial ux partial x dx squared plus partial uy partial x dx squared. And if you work it out, that evaluates to 1 plus 2 partial ux partial x plus partial ux partial x squared plus partial uy partial x squared. Okay? So now, remember I said the deformation is small. So I need to give you let's give you a firm definition of what small means. Okay? So for our purposes, small implies that any gradient of u, the magnitude of any gradient of u, is much, much less than 1. Right? So if this is essentially a gradient of u, right? The gradient of ux with respect to x. So since any gradient of u is going to be small, then these, I have a number that's really small, much less than 1 squared. It's going to be a really tiny number. Same here. So with that, I'm going to ignore these higher order terms. They're going to go to 0. Right? So now I have an expression for AB squared. That's 1 plus 2 partial u of x partial x. Right? So then let's return up here and look at this equation. Right? So now I have something. I have something to put on the left side for AB. Right? Ultimately, I'm trying to get a relationship between the strain, epsilon x, and the displacement. Right? So I'm getting closer. So if I just square both sides of that equation, then I have AB squared on the left-hand side, and I can substitute that in. Right? I'm going to square both sides of that equation up here. Right? And then I'll go over here and complete the work. So then, I have AB squared is equal to epsilon squared plus 2 epsilon x plus 1. Right? And that, according to this, is equal to 1 plus 2 partial u x partial x. So we're almost there. This is one other higher order term, so we're going to ignore it. And now, you can see that the 1's cancel, the 2's cancel, and I have that epsilon x equals partial u x partial x. So all of that just to get the same result we had in 1D, sort of. Yeah. What did happen to that guy? Well, let's just work it out. What did happen to it? So I'm going back to here. So the first term, it doesn't matter, right? So I'd have so the first term's going to be like this thing squared. I don't care about that. That's going to go away. But then I'm going to have 2 epsilon x dx. And the dx squared I don't care about. Okay. It should be there. Should be there. Should be here. But also should be there. Should be a dx there also. Dx there, right? So then these just cancel. Sorry. I'm going to spare you the details, but we could work through. I mean, the whole point of going through all of that, just to say I know it's sort of messy, but it's really just geometry, right? It's just geometry combined with this assumption of small. So then we could do the same exact thing for epsilon y. We can get partial uy, partial y. okay? So that gives us, you know, epsilon x, epsilon y. This is only two-dimensional drawing here, but if it had a third dimension, we could follow the same arguments and get epsilon z. But now we have these shear strains, right? The off-diagonal terms, epsilon xy, epsilon xz, and those guys, right? So what we're going to do is we're going to call this angle right here 2 epsilon xy. And the 2 will be apparent in a second, okay? But, and so this is an alpha there, and that's a minus beta, if you can't see. So then 2 epsilon xy is equal to alpha minus beta, okay? And alpha, just from geometry, right, the opposite over, right, you know, the tangent is the opposite over the adjacent, right? The opposite, so I'm going to take the tangent of alpha. That's the opposite over the adjacent, right? So the tangent is partial u y partial x dx, that's opposite, that's this guy, over the adjacent, which is dx plus partial ux partial x dx. Okay. Now, again on this assumption of small, turns out we can say for small alpha, that implies that the tangent of alpha is approximately equivalent to alpha. So then that just implies that alpha is equal to what's inside there. And I'll simplify it a little bit. But what's inside there is just uy partial x over 1 plus partial u x partial x. So all I did was simplify the numerator, right? I just simplified it, and then I said, okay, for small alpha, then the tangent of alpha is alpha. So alpha is equal to this, right? Now, remember our definition of small is that the gradient of u is much, much less than 1. So I have 1 plus something that's much, much less than 1. That's approximately 1. So we're going to say that this is approximately 1, and then therefore alpha is partial u y partial x. And then you can make likewise for beta. You would get that beta is equal to minus u of x partial y. And so then just plugging in alpha and beta back into this equation, you get that 2xy is equal to partial ux partial y plus partial uy partial x, or epsilon xy is equal to 1/2 ux y plus uy x. Okay, so I know that the 2 there is just a curiosity or a convention at this moment, but it'll be real clear in just a second why we put that 2, right? We just chose to call that 2xy for now. 2 epsilon xy. Right? But then we get this expression. And the reason for the 2 is that so we could go on and basically work through the geometry of all of them. And ultimately we could, if we had a third dimension, we could find all the components. And here I've got it written in terms of 1s and 2s and 3s, but you could just make the analogy that 1 is x and 2 is y and 3 is z. It's just a little more general if you write it like this, because you could use all the equations would still hold in polar coordinates, where 1 would be r, 2 would be theta, and 3 would be another angle. Okay, so so then this is sort of the reason for that convention of the 2, and that is because ultimately we can write the entire strain tensor with this one compact equation for I equals 1, 2, 3, j equals 1, 2, 3. So if you choose an I, 1, plug it in, choose a j, 1, and let's do that real quick. We're almost done. But if we just choose, say, epsilon 1, 1, then you'll see that this is 1/2 partial u 1 partial x1 plus partial u1 partial x1, or 1/2 2 partial u1 partial x1, and the 2's cancel, and so then you just get partial u1 partial x1, or in xy, that to follow the convention we were using, partial ux partial x, right? And you can verify that 2, 2 would give you the same thing. 1, 2 would give you partial u1 partial x2 partial u2 partial x1, or as we were using earlier, ux partial y, uy partial x. Okay? So now we know geometrically what strain is, and next time we'll talk about the relationship between strain and stress.